Good morning. Max, there is not because it hasn't really been tailored much to distance learning. Um, so I feel like it needs to be cut down and trimmed as much as possible before then. So yeah, apologies that there's not. Okay, so let's get started then. Right. From my picture, shall we have a guess as to what the topic is going to be today? Florence, I think it would definitely be a good idea for you to just write things down. Not have it, you don't need to have it be your official note, so to speak, but it helps put it in your memory a lot easier if you're writing things down or drawing things out while you're listening. Because if you're just listening, it could easily just go in one ear and out the other. Um, Whereas when you're writing things down, it's a lot more active then. So just some quick notes would be best just to help you implant it in your head a bit more. And yes, the correct answer is magnetism. So we're going to be talking about how the Earth is magnetic and what a magnet even is. Right, so our first learning objective is to know what a field is in physics specifically. Not like a field as in a field of flowers or anything like that, but specifically in physics, what are we talking about when we say magnetic field or gravitational field? That's the first important thing. Because I'm going to be using the phrase magnetic field quite a bit, I want you to actually have an understanding of what I'm talking about when I say magnetic field. So, oops. Our definition of a field, let me reduce the thickness of my pen because it's a little bit too much. Okay. Our definition of a field. Basically, it's a space where a non-contact force can act. So a force, think back to year 7, a force is basically just a push or a pull. No, not a football field. A force is basically a push or a pull. And normally when it comes to forces, there needs to be some sort of touching involved in order for a force to act. Like for example, with friction, there's no friction unless two objects rub against each other. Um, Another example would be like a force when you're pushing something. You need to be touching that object in order to exert a force on it. But remember, there's also some types of forces that don't require the objects to be touching, yet you still feel some sort of force. And the space in where that non-contact force can act is known as a field. So for example, we have gravitational fields, where the force is gravity, and where the force of gravity can act. Like, for example, when you jump up in the air, even though you're no longer in contact with the ground, the force of gravity is still going to be pulling on you. Florence, I would say it shouldn't take too long, and then I'll set you to some practice. An hour at most. That's saying at most. More likely to be like 40 minutes. Yeah, Evan's spot on with that. So, for example, with gravitational fields, there is a space around like the Earth that's exerting its gravitational pull on you. You can be jumped up, no longer in contact with Earth, yet you're still in the gravitational field, so you still feel the non-contact force of gravity. But if you go further away and leave the gravitational field, so leave the area surrounding the Earth, then the force of the Earth's gravity no longer acts on you. So when we talk about the field, it is a specific space where that non-contact force can act. And we have gravitational, we can have magnetic, and we can also have the electrostatic. So for example, with charges, a plus and a minus charge will be attracted to each other and feel a force towards each other without needing to be touching. There's a space in which that can happen. Same with magnets. You put them close enough to each other and then you feel that attraction or that repulsion. But if they're super far away, no longer in each other's fields, then you won't have that force anymore. So it is a specific space as to where a non-contact force can act, and today we're going to be mostly focusing on this one, the magnetic field around a magnetic object. Right, another key phrase. Yes, Max, I am. To make it clear that it is an assessment, but it is going to be the multiple choice show my homework quiz. So our second learning objective is knowing what a magnet is. You obviously would have heard of the term magnet before, just in daily life, or back in Key Stage 2, or back in Year 7. Most of you would have some understanding of what a magnet is, but once again, as we get to later stages of your learning, we need to have a proper definition for what a magnet is. And basically, a magnet is an object, that's the first thing. It is something, it is an object that can produce a magnetic field, I would say. And examples is we have iron, nickel, and cobalt. So not every single object can actually produce a magnetic field. A piece of paper is not going to be producing a magnetic field. Evan, I haven't put up the space one yet, so it's not up yet. So with a magnet, it is basically just an object that can produce a magnetic field. Not every object can do that, but we have three metals that can. Iron is used for magnetic materials because it can produce magnetic fields. Same with nickel, same with cobalt. Best way to memorize this, I think, is just ink. Ink. So we talked about what a magnetic field was, and then a magnet is just something that can produce this magnetic field. But I just want to make it clear that this isn't something that scientists have just made up one day. You can actually see the magnetic field of an object surrounding a magnet when when you when you sprinkle on, say, like for example, iron sand. So here we have like a bar magnet. We would have done this experiment in class, but if you have me next year, we will definitely do it at some point just for you guys to see. What this picture shows is basically we had a bar magnet and we had some iron filings, which is basically just small bits of iron that's been ground up into like a powder so that then it could be easily sprinkled. And when sprinkled all around this magnet, it produces this image. It makes this shape. That wasn't, by human design. This was a natural phenomenon where it naturally produced this shape. And these sort of indicate that there are certain points of the magnet where the magnetic field is stronger. Like you'll notice that the iron filings is experiencing like more of an attraction at the poles because there's more of them here. Look how concentrated there are. And then another thing I want you to notice is that it sort of makes this shape like, it arches upwards. We're going to draw this properly in a second, but I just want you to pay attention to what we actually see here, this pattern. And we call this pattern the magnetic field lines. So we're not making it up when we draw things like a magnetic field. This is actually something that can be observed. So, thinking about a magnet then. When we talk about magnets, we come across a word called poles. And you guys would have heard of something called the North Pole and the South Pole. Not just geographically, meaning like, the Earth's North Pole and the Earth's South Pole, but also north and south in terms of magnet. A magnet has one North Pole and one South Pole. But one thing that I do want you guys to be aware of is North Pole is actually short for something else. We call the North Pole the north-seeking pole. This will be important in a second, and the South Pole is the south-seeking pole. These two here are actually the proper full names of the North Pole and South Pole. On a magnet, this is. But we shorten it to just saying North Pole of the magnet, South Pole of the magnet, when really the long full name of it is North-seeking pole, South-seeking pole of the magnets. And remember, I'm not talking about the Earth here, I'm talking about magnets specifically. Now, what happens when you put different poles together? I have this picture right here just to show you. When you put opposites together, like a South Pole and a North Pole, there's an attraction there. Because they're opposites, opposites attract. North attracts south, south attracts north. So we have these arrows just drawn to show that attraction, where the South Pole is going towards the North Pole, it's attracting and being pulled towards the North Pole, and vice versa, North Pole being pulled towards the South Pole. However, if you try to, if you put two of the same types of poles together, so south meeting south or north meeting north, you experience a repulsion. And you could do this easily at home with fridge magnets by just flipping over the magnet if you to get the two of the same poles facing each other, and then you experience a non-contact force that is repelling the two magnets apart because they're the same type of pole facing each other. So once again, the arrows are trying to show this, where the south is being repelled, same with the other, North being repelled, same with the other. So, opposites attract, same repel. That's the main key thing you have to be aware of. Opposites attract, same repel. And this we'll go into more detail on this in a second, because this is important for our next thing that we have to be aware of. Okay, now this is where it gets confusing. When we talk about the North Pole of the Earth, it's at the very top of the Earth, right, where Santa is. That's known as geographic North Pole, because that's what we call it, being the North Pole. But in terms of it being a magnet, the Earth's North Pole is actually the South Pole, or the south-seeking pole. Now that is where it's so important that on a magnet, the North Pole is north-seeking. Why I needed to tell you the full names. The South Pole is south-seeking. Because geographic north, so the actual North Pole where Santa is, because it's the North Pole, it would be attracted to the South Pole. So it is south-seeking, so it's magnetically south. Let me say that again, because this is where a lot of people get confused. On geographic north, it is south-seeking, so we call it the South Pole in terms of a magnet. So geographic poles and magnetic poles are actually completely different, and they're opposites to each other if you think about it. So that is why when you have like a little compass, right? A compass points north, always points to geographic north. And the reason why it points to geographic north is because the arrow inside your little compass is actually the north, is a north-seeking pole. And because it's north-seeking, it's going to be pointing to a south-seeking pole, which is at the top of Earth. How are we with that? I just want you to write in the chat, because it's gone silent a second, the difference between geographic north and magnetic north, because geographic north is different to magnetic north. Okay. Right, let me explain further with a compass. Oh, let me get rid of this. So on our compass, the little arrow bit, this bit here, this is the north-seeking pole. The opposite end on that compass is the south-seeking pole. Right. So, Evan, when we say that it's the north-seeking pole, what do we call that? What do we shorten the north-seeking pole to? Yeah, so it's the north-seeking pole. We call it a north pole, and that's magnetic, and south-seeking pole would be called the south pole. But when you use a compass, it points to geographic, and when I say geographic, I mean like what we usually call where the North Pole is on Earth, geographic north. So it points to like the top of Earth when you use a compass. But knowing what we just learned about attraction and repulsion, it shouldn't make any sense that a North Pole on our compass magnet is pointing to the North Pole of Earth, because remember, the same ones are supposed to repel each other. Let me write that out. Because you might think, well, my compass is a North Pole, but it shouldn't then be pointing to the North Pole because the same ones are meant to repel. And the reason being for that is because even though we call on Earth the North Pole, that's actually a magnetic South Pole. So your compass is actually pointing to the magnetic South Pole on Earth. So, in terms of the diagram, this diagram on the left-hand side basically is just showing that the Earth, as it spins, it's generating a magnetic field. That's it. But when it's generating this magnetic field, the top of Earth where the geographic North Pole is, so this bit has Santa. This bit down here has the penguins. So where we call the North Pole in daily life, in terms of a magnet, if you think of Earth as a giant magnet, it is actually magnetically a South Pole. That explains why the North Poles of our compass is attracted to the North Pole of Earth, because the North Pole of Earth is actually a South Pole in terms of a magnet. So if your compass says you're walking south, you're walking to the north. You are walking to the south geographically, but you're walking towards the North Pole of a magnet. It's completely natural for us to be confused because in terms of language, we've messed this up completely. Because like back in the day, explorers called the North Pole of Earth the North Pole, and the South Pole of Earth the South Pole, and that was what stuck in terms of geography, what we call it when we talk about different locations on the Earth. That's what's stuck. But then as science advanced, we realize, wait a second, actually, the North Pole of Earth is actually, if we think about Earth as a giant magnet, it's actually a South Pole. And so now we have two different things going on here. Let me just answer your question. So I'm not walking south, even though my compass says I'm walking south. I'm walking north. Okay, Evan, I think what you need to separate in your mind, this is the key, okay? This is the key. Take a step back, and in your mind, separate geographic poles from magnetic poles. Geographic poles is what we call when we just label the Earth and we say here's the North Pole of the Earth, here's the South Pole of the Earth. North Pole is where Santa is, South Pole is where Penguin is. where penguins are, right? That's geographic. That's us describing, that's on maps. So all of the maps that you see and everything, that's all to do with geographic north. Are we okay with that? So maps, north, south, east, west, that's geography. Geographic north. But the Earth is actually a giant magnet. Because its core is actually made out of iron and it's spinning. Basically, it's a giant magnet. It produces a magnetic field. And what we ended up observing was that the North Pole, where we have been calling it the North Pole, where we've been labeling it on maps as the North Pole, yeah, that fits in terms of geography. But in terms of the Earth being a giant magnet, it is actually a south pole, south magnetic pole. So geographic north is magnetic south, and geographic south is magnetic north. So there's two separate ways that we talk about poles. We talk about south poles and north poles in terms of magnets, and we talk about south poles and north poles in terms of geography. And now, in your everyday usage, you're going to be talking about the geography one because that's what we experience. I don't want you guys to start flipping your maps upside down. But in terms of us understanding how compasses work and how magnets work, it is important to understand that it's the opposite way around in terms of magnets. It's because it's left the field then. And not everything that's made out of metal is actually going to be experiencing a magnetic force. Not all metals experience a magnetic force. What do you mean, how does this affect ionizing radiation? Magnetism isn't a form of ionizing radiation, so it doesn't affect it. I mean, there's like electromagnetism, but it's not really. The main things of ionizing radiation, I don't want to confuse people, but it's like X-rays, gamma rays, and UV rays, and also alpha, beta, gamma radiation. It's not relevant to this. Okay, so, right, back to our learning objectives now. So I'm glad we've hopefully cleared that up when we talk about North Pole and South Pole in terms of geography. That's completely fine, but we do have to understand that in terms of a magnet, it's the opposite way around for Earth. That's the key bit. Oh, yes. Do you mean from the sun? Right, Evelyn, I'll go into that in a second, but I don't really want to confuse other people at the minute. The Earth's, there's a lot of interesting things we can go into about the Earth's magnetic field. Like, for example, the Earth's magnetic field is responsible for the aurora borealis, things like that. But I'll get to it in a second once I've sorted everyone else out. Okay, so make sure that you know this pattern, because this is how we draw magnetic field lines. If we were to draw our magnet here with a north and a south, remember the picture that I showed you earlier with the magnetic field lines that we observe? Remember how I showed you that it's stronger, it's more concentrated at the ends, at the poles. And so when we draw our field lines, notice how the field lines are a lot more concentrated at the poles. So this is how you draw it. And when it comes to arrows, our magnetic field lines, the arrows leave the North Pole and are attracted to the South Pole. So let me draw this from scratch just to show you what you need to be able to draw. Blank. Okay. So you don't need to go super complex and make it absolutely beautiful. You know what? Let me flip this around. I'll put north by there. Okay. So first things first is, let's pretend we had a magnetic field line. It has to leave the North Pole and go to the South Pole. So my arrows would be by there. Notice that over by here there's other lines that are curving outwards as well, but they're all leaving the North Pole, going towards the South Pole. You could just do it like that. Draw another one. And all arrows are pointing towards the South Pole. So if I were to draw another one at the bottom there, it has to once again leave North Pole, point towards South Pole. Draw another one. Oops, that's a little bit wobbly, but leave North Pole, point towards South Pole. One of the biggest mistake I see is that some students, they get the arrow the wrong way around on the bottom hand side, but you need to make sure that all of the arrows point towards the South Pole and away from North. So all the arrows should do that, and that should be fine. You don't have to go into making the picture beautiful or anything like that. You just need to have the arrows going in the right direction and get the general shape of the magnetic field correct, which is that arched shape. Okay, so just some more magnetic field lines just to show you. So we have, once again, you don't have to draw like these ones here. You can if you want to, but you would still have the general idea even with the basic field lines drawn. So all arrows away from north towards south, away from north towards south once again, which is why there's that attraction. But when you have two norths together, you have away from north, but there's no point where they have that attraction, so they repel. Oops. Okay. Hold on, let me just check out questions. Right. So, for a bit of practice now, and then I'll answer Evelyn's questions. Let me link you quickly to our website. There we go. Okay, if you scroll down to Earth and Space, and you click on Magnetic Earth, there should be two documents, one with the questions and one with the answers. Once again, this is completely optional, so don't feel like you have to do this. The only thing that you need to hand in is assessments. So you don't have to do this at all. This is just for you to help develop some confidence in what you're doing. So the first set of questions is basically just whether or not they will repel or attract. So you don't need to go into detail as to why, just identify whether the magnets will repel or attract. Question 2, why is one end of a bar magnet called the north-seeking pole? Because it's pointing towards geographic north. Question 4, drawing field lines. And I have the answers to it on the second document, just for you to check your answers yourself. And while you guys are having a look at that, just to answer Evelyn's question, you are correct that the Earth's magnetic field can block high energy particles. And the interesting thing is, here, let me just find you the link to... Where is it? There we go. So another interesting thing is that the Earth's magnetic poles can actually reverse. And so when that reverses, then geographic north will now become the same as magnetic north, and we won't have the confusing bit. Okay, so guys, I'll let you have a go at the practice now. That should be it for today, so I won't keep you any longer. Check the work that you have done, and in terms of future lessons, we have 2 more, gravity and beyond the solar system, and then we'll do our multiple choice quiz assessment. That was literally just a quick link, Evan, just to give to Evelyn as she asked the question. And so it's an interesting little point about the Earth's reversal, the magnetic field of Earth reversing. Right, guys, I'll see you next week. And have a good rest of the day. Make sure that you go to the first link to check the answers. And have a go at those practice problems, check your answers, and hopefully then we develop a bit more confidence in what we're doing.